Yes, advancements have been made in wire and insulation materials, notably the emergence of cross-linked polyethylene, also known as XLP, and high-temperature polyvinyl chloride, or HT-PVC, both boasting elevated temperature ratings. The primary reason terminations on the majority of devices are capped at 60 or 75 degrees Celsius, despite the wire itself being rated for 90 degrees Celsius, is rooted in safety considerations. Terminations generally consist of materials less resistant to heat compared to the wire. Employing a wire with a temperature rating surpassing that of the termination introduces the risk of overheating, potentially leading to failure and posing a fire hazard. Currently, electrical codes do not mandate terminations to be rated for 90 degrees Celsius. This stems from the fact that the bulk of electrical devices aren't engineered to function at such high temperatures. However, exceptions exist in certain applications, such as high-power industrial motors, where high-temperature wire and terminations are a necessity. In practical scenarios, it is common practice for electricians to derate THHN wire to align with the 75 degrees Celsius column, even when utilizing terminations rated for 90 degrees Celsius. This measure serves as an additional safety buffer, accommodating potential heat accumulation within a termination. Whether to derate THHN wire to the 75 degrees Celsius column is contingent on several influencing factors, including the specifics of the application, the surrounding ambient temperature, and the type of termination employed. As a general principle, exercising caution and derating the wire is advisable, particularly in demanding applications. When dealing with electrical installations, adherence to the National Electrical Code, or NEC, is paramount. The NEC provides tables and guidelines that dictate the allowable ampacities of conductors based on their insulation type and operating temperature. These ampacity values are established under specific conditions, and adjustments, or derating, may be necessary to account for factors such as ambient temperature and the number of current-carrying conductors in a raceway. THHN wire, which stands for thermoplastic high heat resistant nylon coated, is a common type of building wire used in electrical systems. It is known for its good heat resistance and is typically rated for 90 degrees Celsius in dry locations. However, the NEC stipulates that the ampacity of THHN wire must be determined based on the temperature rating of the terminations to which it is connected. Terminations, such as those found on circuit breakers, switches, and receptacles, are typically rated for either 60 degrees Celsius or 75 degrees Celsius. The lower of these two temperature ratings must be used to determine the allowable ampacity of the THHN wire. This is because the terminations are often the weakest link in the electrical circuit and are more susceptible to overheating than the wire itself. When the terminations are rated for 60 degrees Celsius, the ampacity of the THHN wire must be determined using the 60 degrees Celsius column in the NEC ampacity tables. Similarly, when the terminations are rated for 75 degrees Celsius, the ampacity of the THHN wire must be determined using the 75 degrees Celsius column in the NEC ampacity tables. Even though the THHN wire itself is rated for 90 degrees Celsius, the ampacity cannot exceed the value corresponding to the termination temperature rating. This ensures that the terminations do not overheat and potentially cause a fire hazard. In situations where the ambient temperature is higher than 30 degrees Celsius, or when there are more than 3 current-carrying conductors in a raceway, the ampacity of the THHN wire must be further derated. The NEC provides specific derating factors that must be applied in these situations. The derating factors reduce the allowable ampacity of the wire to account for the increased heat generated by the higher ambient temperature or the presence of multiple conductors. The derating factors are applied to the ampacity value obtained from the NEC ampacity tables based on the termination temperature rating. For example, if the terminations are rated for 75 degrees Celsius and the ambient temperature is 40 degrees Celsius, the ampacity of the THHN wire must be derated by a certain percentage, as specified in the NEC. Similarly, if there are more than 3 current-carrying conductors in a raceway, the ampacity of the THHN wire must be derated by another percentage, as specified in the NEC. The overall goal of derating is to ensure that the temperature of the wire and terminations does not exceed their rated values, even under adverse conditions. By derating the ampacity of the wire, the amount of current that can flow through the circuit is reduced, which in turn reduces the amount of heat generated. This helps to prevent overheating and potential fire hazards. In some cases, it may be necessary to use a larger size THHN wire in order to compensate for the derating. For example, if the ampacity of a 12 American wire gauge THHN wire is derated to 15 amps due to high ambient temperature, it may be necessary to use a 10 American wire gauge THHN wire, which has a higher ampacity rating, in order to carry the required current. The selection of the appropriate size THHN wire should always be based on the calculated ampacity after derating and should comply with all applicable NEC requirements. It is also important to ensure that all terminations are properly torqued to the manufacturer's specifications. Over-tightening or under-tightening terminations can lead to overheating and potential failure. Torque wrenches should be used to ensure that the terminations are properly tightened. In addition to following the NEC requirements, it is also important to follow good electrical practices when installing THHN wire. This includes properly stripping the insulation from the wire, making sure that the wire is properly inserted into the terminations, and avoiding sharp bends in the wire. Sharp bends can create stress points in the wire, which can lead to overheating and potential failure. It is also important to protect the THHN wire from physical damage. The wire should be installed in a conduit or raceway to protect it from abrasion, impact, and other potential hazards. The conduit or raceway should be properly supported and secured to prevent it from sagging or moving. When working with THHN wire, it is important to use the proper tools and equipment. This includes wire strippers, crimpers, and torque wrenches. Using the wrong tools can damage the wire or terminations, which can lead to overheating and potential failure. It is also important to wear appropriate personal protective equipment, such as gloves and safety glasses, to protect yourself from electrical shock and other hazards. Working with electricity can be dangerous, and it is important to take all necessary precautions to ensure your safety. If you are not comfortable working with electricity, it is best to hire a qualified electrician to do the work. A qualified electrician will have the knowledge, skills, and experience necessary to install THHN wire safely and correctly. In summary, when working with THHN wire, it is important to consider the temperature rating of the terminations, the ambient temperature, the number of current carrying conductors in a raceway, and all applicable NEC requirements. By following these guidelines, you can ensure that the electrical system is safe and reliable. The NEC provides clear guidelines for conductor ampacity and derating. Firstly, conductors must be suitable for the operating conditions. This means selecting the correct wire type and size for the application. Secondly, the ampacity of a conductor is determined by its insulation type and temperature rating, as found in NEC Table 310.15b16. Thirdly, terminations play a crucial role. Equipment is typically listed and labeled with temperature ratings for terminations. The conductor ampacity used in calculations cannot exceed the lowest temperature rating of any connected termination, as per NEC 110.14c. Fourthly, ambient temperature correction is necessary. If the ambient temperature differs from 30 degrees Celsius, correction factors from NEC Table 310.15b16 must be applied. Fifthly, conductor derating for multiple conductors in a raceway or cable is required. When more than 3 current carrying conductors are grouped together, the ampacity must be derated according to NEC Table 310.15b3. Sixthly, voltage drop calculations are essential. Conductors must be sized to minimize voltage drop, ensuring proper equipment operation. The NEC recommends a maximum voltage drop of 3% for feeders and 5% overall. Seventhly, continuous loads require special consideration. For continuous loads, defined as loads that operate for 3 IOs or more, the overcurrent protection device and conductors must be rated for 125% of the continuous load, as per NEC 210.19 AON and 215.2 AON. Eighthly, conductor identification is important. Conductors must be properly identified with color coding or other markings, as required by NEC 310.8a. Ninthly, conductor installation practices matter. Conductors must be installed in accordance with NEC requirements, including proper support, protection from physical damage, and separation from other systems. Tenthly, regular inspections and maintenance are vital. The electrical systems should be regularly inspected and maintained to ensure they are operating safely and efficiently. In the specific case of THHN wire, remember that while the wire itself may be rated for 90 degrees Celsius, the termination temperature rating often dictates the maximum ampacity you can use. Always consult the equipment labeling and the NEC tables to determine the appropriate ampacity and derating factors for your specific installation. Using high temperature rated conductors like THHN provides a safety margin and allows for future load increases as long as the terminations are not exceeded. The development of wire insulation materials like XLPE and HT-PVC has significantly improved the performance and safety of electrical systems. These materials offer several advantages over traditional insulation materials, including higher temperature ratings, improved resistance to moisture and chemicals, and increased flexibility. XLPE, or cross-linked polyethylene, is a thermosetting polymer that is widely used as insulation for power cables. It is produced by cross-linking polyethylene molecules, which creates a three-dimensional network structure that improves the material's strength, heat resistance, and chemical resistance. XLPE insulation can withstand temperatures up to 90 degrees Celsius in continuous operation and up to 130 degrees Celsius in emergency overload conditions. This makes it suitable for use in high-temperature applications, such as those found in industrial plants and power generation facilities. HT-PVC, or high-temperature polyvinyl chloride, is another type of insulation material that is commonly used for electrical wiring. It is a thermoplastic polymer that is modified to improve its heat resistance and flexibility. HT-PVC insulation can withstand temperatures up to 75 degrees Celsius in continuous operation and up to 90 degrees Celsius in short-term overload conditions. This makes it suitable for use in a wide range of applications, including residential, commercial, and industrial wiring. One of the key advantages of XLPE and HT-PVC insulation is their improved resistance to moisture and chemicals. These materials are less likely to absorb moisture or react with chemicals than traditional insulation materials, which helps to prevent corrosion and degradation of the conductors. This can extend the life of the electrical system and reduce the risk of failures. Another advantage of XLPE and HT-PVC insulation is their increased flexibility. These materials are more flexible than traditional insulation materials, which makes them easier to install and work with. This can save time and money on installation costs. In addition to their improved performance characteristics, XLPE and HT-PVC insulation are also environmentally friendly. These materials are recyclable and do not contain any harmful chemicals. This makes them a sustainable choice for electrical wiring applications. When selecting wire insulation materials, it is important to consider the specific requirements of the application. Factors to consider include the operating temperature, the ambient temperature, the presence of moisture or chemicals, and the required flexibility. It is also important to consult the NEC and other applicable standards to ensure that the selected insulation material meets all safety requirements. In addition to XLPE and HT-PVC, there are other types of wire insulation materials available, such as rubber, silicone, and fluoropolymers. Each of these materials has its own unique properties and is suitable for different applications. Rubber insulation is commonly used for low-voltage wiring applications. It is flexible and has good resistance to moisture and abrasion. Silicone insulation is used for high-temperature applications, such as those found in ovens and furnaces. It can withstand temperatures up to 200 degrees Celsius. Fluoropolymer insulation is used for applications where resistance to chemicals and extreme temperatures is required. It is commonly used in the aerospace and chemical industries. The selection of the appropriate wire insulation material is critical for ensuring the safety and reliability of electrical systems. By carefully considering the specific requirements of the application and consulting with qualified electrical professionals, it is possible to choose the best insulation material for the job. Remember that derating practices are essential for ensuring the safe and reliable operation of electrical systems. By properly derating conductors and terminations, it is possible to prevent overheating and potential fire hazards. Always consult the NEC and other applicable standards to determine the appropriate derating factors for your specific installation, and always err on the side of caution, especially in demanding applications. The selection of appropriate overcurrent protection devices, such as circuit breakers and fuses, is also crucial for protecting electrical systems from overloads and short circuits. These devices are designed to interrupt the flow of current when it exceeds a certain threshold, preventing damage to the wiring and equipment. The size of the overcurrent protection device must be carefully selected to match the ampacity of the conductors and the rating of the equipment. Using an overcurrent protection device that is too large can allow excessive current to flow through the circuit, which can lead to overheating and potential fire hazards. Using an overcurrent protection device that is too small can cause nuisance tripping, which can disrupt the operation of the electrical system. The NEC provides specific guidelines for selecting the appropriate size overcurrent protection device for different types of circuits and equipment. It is important to follow these guidelines carefully to ensure that the electrical system is properly protected. In addition to selecting the appropriate size overcurrent protection device, it is also important to ensure that the device is properly installed and maintained. The device should be installed in a readily accessible location and should be properly labeled to indicate its function. The device should be inspected regularly to ensure that it is in good working condition. If the device is found to be damaged or malfunctioning, it should be replaced immediately. Proper grounding is another important safety measure that must be taken in electrical systems. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip the overcurrent protection device and prevent electrical shock hazards. The grounding system must be properly designed and installed to ensure that it is effective. The NEC provides specific requirements for grounding electrical systems, including the size and type of grounding conductors, the location of grounding electrodes, and the bonding of metal enclosures. It is important to follow these requirements carefully to ensure that the electrical system is properly grounded. In addition to proper grounding, it is also important to use ground fault circuit interrupters, also known as GFCIs, in areas where there is a risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. GFCIs are designed to detect small amounts of current leakage to ground and to interrupt the flow of current before it can cause a serious injury. GFCIs are required by the NEC in many locations and are an essential safety device for protecting people from electrical shock hazards. Regular inspections and testing of electrical systems are also important for ensuring their safety and reliability. Electrical systems should be inspected regularly by qualified electrical professionals to identify any potential problems, such as loose connections, damaged wiring, or malfunctioning equipment. Testing should be performed to verify the proper operation of overcurrent protection devices, GFCIs, and other safety equipment. Any problems that are identified during inspections or testing should be corrected promptly to prevent potential hazards. Electrical safety is a shared responsibility. Everyone who works with electricity should be aware of the potential hazards and should take precautions to protect themselves and others. By following safe work practices, using appropriate personal protective equipment, and complying with all applicable electrical codes and standards, it is possible to prevent electrical accidents and injuries. Continuous education and training are also essential for maintaining electrical safety. Electrical professionals should stay up to date on the latest codes, standards, and technologies. They should also participate in regular training programs to refresh their knowledge and skills. By investing in education and training, electrical professionals can ensure that they are competent and qualified to perform their job safely and effectively. The use of arc fault circuit interrupters, also known as size, is another important safety measure for protecting against electrical fires. size are designed to detect arc faults, which are dangerous electrical conditions that can cause fires. Arc faults can occur when there is a break or weakness in the insulation of a wire, which allows current to arc across the gap. The heat generated by the arc can ignite nearby materials, such as wood or paper, and start a fire. SIs are required by the NEC in many locations, particularly in residential wiring. They are designed to trip the circuit breaker when an arc fault is detected, preventing the arc from causing a fire. The proper installation and maintenance of electrical equipment are also essential for preventing electrical hazards. Electrical equipment should be installed in accordance with the manufacturer's instructions and all applicable codes and standards. The equipment should be properly supported, grounded, and protected from physical damage. Regular maintenance should be performed to ensure that the equipment is in good working condition. This includes cleaning, lubricating, and tightening connections as needed. Any damaged or malfunctioning equipment should be repaired or replaced immediately. Proper lockout/tagout procedures are also important for protecting workers from electrical hazards during maintenance and repair work. Lockout/tagout procedures are designed to prevent accidental energization of equipment while it is being worked on. These procedures involve disconnecting the equipment from its power source, locking out the disconnect switch, and tagging the switch to warn others not to energize the equipment. Lockout/tagout procedures should be followed whenever electrical equipment is being serviced or repaired. Electrical safety audits are a valuable tool for identifying potential hazards and improving electrical safety practices. Electrical safety audits involve a systematic review of electrical systems and procedures to identify areas where improvements can be made. The audit should be conducted by qualified electrical professionals and should cover all aspects of electrical safety, including wiring, grounding, overcurrent protection, lockout/tagout procedures, and training. The results of the audit should be used to develop a plan for correcting any identified deficiencies and improving electrical safety practices. Electrical safety is a continuous process that requires ongoing attention and effort. By implementing these safety measures and promoting a culture of safety, it is possible to create a safe and reliable electrical environment for everyone.